Okay, shall we start? Okay. Yes. Yes, last week we were discussed the key ideas behind bounded SAT-based model checking. And I also did introduce the concept of inductive invariance. So let me quickly recap the bounded SAT-based model checking, the ideas behind it. Here, the one key idea is to exploit the fact that counterexample to an LTL, CTL, or incidence is in a finite Kripke model is either a finite length path or is lasso shaped. Okay, so that is the key observation that is exploited, so that now then you could so then you could maybe enumerate longer and longer lassos, lassos, and then check if they are if that is a counterexample. Okay? So, for example, if you have a GP-like property, that's as I said, we primarily start doing this for safety and maybe simple liveness, and mainly we concentrate on safety. So then, you can make an instance of a propositional formula of this kind, which checks if this is a counterexample of some of length k to the property G of P, where P is a predicate. Okay, so there is a path part and a property checking. So if there is a satisfying instance of it, then it says that there is that's a counterexample. For checking liveness of the formulas of the form f of p, because witness to this violation of this has to be an infinite path, and every counterexample is lasso shaped. Therefore, this thing. So let me ask you, I mean, we discussed this a little bit at length. Paramalai, why should a counterexample always be of a lasso shaped to an LT or a CTL formula?
For this specific formula FP, that's the way we will show that FP is not set. We cannot give a regular counter example for just the finite path. We have to show there exists an infinite path such that.
Yeah, that is true. Yes, the counterexample with this is infinite, correct. But why should it be lasso shaped? See, a lasso shaped assumes that there is a tail, a finite tail. After that, there is the loop. And then after that, there is a certain finite pattern that repeats itself. Okay? Yeah. And I think the key thing is, see, a Kripke structure can have parts that are not repetitive. I mean, I will show very soon. But as I said, we constant both LTL and omega regular properties are defined this way. Okay. Therefore, even if therefore, because our property specification language is either LTL or in the case of omega regular properties, we saw that those properties themselves are structured this way. Therefore, the violation to those properties are always this shape. Now, in a particular Kripke structure, there can be paths which may not be, you can construct a lasso out of it. They may not be lasso. I will show you an example, but they are for our property specification language. They don't distinguish between these, so even if there are paths which are infinite paths, which may not be lasso shaped. A lasso shaped path means after, the only way you can make infinite paths is after a finite tail, you repeat these things, okay? So, but our specification language is such that, it is enough to consider these kinds of paths. That is why I keep insisting that a counterexample to a property is always of this kind, okay? Because our property, I showed you, I defined you what omega regular properties was. And I also, without proof, showed you that LTL is a restriction over these omega regular properties. And those properties were actually defined like this. And that's why you have this result. Do you get that point?
Yes, sir.
Okay. I will show you an example as to why, although Kripke structure can have non-lasso shaped path, they would be indistinguishable, in the property specification language that we actually use. Okay, so that is important, for you to keep in mind and understand. And that's what this thing is done. So in order to check simple liveness, you, in addition to having this path constraint, you also need to ensure that you have reached a lasso. And the lasso part says that, the state at SK, at the kth point, you've already seen at some point before. Okay, so this is what I call as a LK lasso. Okay, it's this K long lasso with the loop part looping back to the L position. Okay, and P should, not P should be continuously true in all these states. Then you have found an infinite path on which P never holds good. Therefore, in addition to the GP-like thing, that loopness condition is not required, because as soon as you find a violation, a finite prefix, you can stop. Whereas for liveness property, you need to find an actual lasso. Okay, so in general, you have. So there is what I call as a bounded model checking part, which asserts that there is a path, okay, of length k from an initial state. This characterizes a k-long path from an initial state. And then there is a lasso-ness check. It says that the kth, there is yeah, this is actually not true. Okay, so this should be pairwise disjunction. Okay, like I've pointed out here, that k can be equal to any one of the states from S0 to Sk. Okay, so this should be a this is not correct. Okay, there is a BMC k part. The loop KL, I'm sorry, I made a mistake here. This should just be this part here, okay, which is pairwise disjunction that compares SK to any one of the states. That defines a lasso. And then there will be, of course, the property part. Okay, so that is, in general, is what you have. Okay, now. Forget about the recurrence diameter and so on. See, these are, look at this example. There are various lassos here. See, a lasso doesn't require that you have, the finite prefix part can have repeated states. Okay, so all a lasso requires is that there is a loop back. Okay, the kth part, the kth state you've already seen. Okay, so sometimes a lasso, we distinguish between two kinds of lasso: a pure lasso and an impure lasso. A pure lasso is one in which there is no repetition of the state in the prefix, the initial prefix part of it. Okay, so so for example, here there are, if this is the transition system, you can find lots of different kinds of lassos here, right? So you can like I've shown here. So you can have, a pure lasso is one, like this. So it goes from here and then it, keeps repeating. Or you can, for example, traverse some finite number of iterations through the first two loops, okay? And then after that, you can end up with a lasso. For example, here in the first two, you can have traverse it a finite number of times, and then you can go to 3, and then you can repeat, that thing. So that will have some repeated states in your prefix before you actually lasso to repeat a particular finite. So I'm just making that observation. So that sometimes is called impure lassos, that where you can have some repeated states in your finite prefix part before the looping part of the lasso. Okay, so going back to my previous points, see, you can also have an infinite path which is not lasso shaped. For example, you can have paths in which you cycle around a certain number of times in your first thing. You can see the cursor, right, guys? My cursor moving?
Yeah.
Yes, sir.
Yeah. So you can move, you can cycle here for a certain number of, sometimes then in this, and then you can go back and circle one more time here and one more time here. See, that is also a path, okay? So that's why not all paths in a Kripke model have to be lasso shaped, but our property specification language is such that it really doesn't distinguish, okay, any property that, that is true of that kind of a path which is not lasso is actually equivalent. It's not distinguishable. It is indistinguishable from something which corresponds to a particular lasso. So that's why. So there is this question. Okay, if you ask, not all paths in a finite race transition system have to be of that lasso shape, because I can actually have, like I just now explained. Did you see? Did you appreciate the difference? The point that I made?
Yeah. Yes.
Yeah. So the point is that while you can have those things, there are two important points, and I think I keep repeating this, and that's important, that it is the property specification language that doesn't distinguish. Okay, and that's why you can consider this path, the lasso shaped path, because the kind of path in which there is no pi which keeps repeating itself. It has to be generated by one of the lassos. Okay, so if you prove that property for one of the lassos, the violation of the property, then you would have proven for non-lasso like execution also. That's why it is good enough, because a property specification language is such that it can only distinguish can only specify things of the lasso shape thing, and it is good enough for us to yes, of this. Yeah, so that's why we look at these. That's why the claim is that any counterexample to that thing is always lasso shape, and therefore it is enough for us to kind of enumerate lasso shaped execution paths to check violation of those things. So with that, you can use bounded SAT-based model checking in an incomplete way, okay, as shown by this flow chart, which we saw yesterday, okay, in which you enumerate longer and longer paths, okay, from the initial state, incrementally longer and longer path, and see if you have reached a counterexample. Or you can also make it complete if you can come up with what is called the completeness threshold. I will formally define what a completeness threshold is. If you can, come up with a bound after which bound on the length of the lasso-shaped paths on the counterexample, lasso-shaped counterexamples paths. There's a bound on some metrics on that lasso-shaped path that will guarantee that that is after which you won't find any counterexamples to that property. Then you can also make this kind of model checking, this SAT-based model checking, complete. Okay. See, what is unique here is we are only considering increasingly longer paths. We are not doing existential quantification elimination, which is needed for this. Therefore, okay, this is not what I want to show now. So I will go to this one. So like I said before, so after this, so this is an incomplete way of doing it, okay? Which can be a thing. So can you make it, how do you, what are the ways in which you can make this thing complete? This basic idea of enumerating longer and longer, search for counterexamples, can you come up with some kind of a complete method? Okay. So there are three ways of doing it. Okay. We started talking about induction. So I'm taking a step back and then saying that there are other ways of doing it as well. You can find bounds on the maximal length of counterexamples. And that's what is called the completeness threshold. Okay. There, it may be very hard to find exact bounds, but maybe you can come up with some looser bounds on the maximal length of the counterexamples. And then if you did, then looser bound on the completeness threshold. And if you are able to do that, and usually these bounds are, they are dependent on the structure of the transition system, how the states are connected by the transition relation, and also is dependent on the structure of the property, the formula that is being checked. So that is one way to do. So before I continue describing the induction methods, okay, which I started last time, I want to spend briefly a little bit time of how defining some completeness threshold for safety and simple liveness property. Okay, that is one way to complete. Or you can use induction. Okay, induction, which actually checks if we have reached some kind of a fixed point. Of course, you can use the standard BDD-based methods that you are working on by explicitly eliminating existential quantification, and then use the same fixed point computation. Instead of using BDDs, you can use SAT. And what we are trying to do is to avoid that. And why is it that we're trying to avoid? Amin? Hello? Are you there? Did you hear my question?
Okay, you were asking about this one, right? Why we use, why we want to eliminate this fixed point computation.
Yeah, I mean, see, you could do exactly what you did with BDD by taking existential quantification elimination. Okay, and then still continue to use SAT.
We
What?
rejected that because for larger formulas, BDDs become hard to handle. Right?
No. For larger formulas,
BDDs might grow very large. Right?
that is the reverse. Okay, I mean, you can't use this method of enumerating counterexamples because they involve various. I asked the reverse question. Why can't, what is the disadvantage of why not do fixed point computation? Image-based fixed point computation using SAT solvers. Okay.
Oh, okay.
Now, and the reason is, I already explained that, and the reason is then you'll have to do existential quantification elimination in each step. Okay. So if you're using SAT solvers, SAT solvers always work with CNF formulas, and if you use existential quantification elimination, you don't have pretty soon those images. Okay, formulas representing those images in CNF form can really explode. Okay, that's why you don't want to do that. SAT solvers are good for solving even formulas which don't have doing existential quantification elimination. Will if you try to eliminate existential quantification, quantifiers and still keep it in CNF form, you have to do OR, okay, over ANDs, distribute OR over AND, and so on. And the CNF will be too big, okay. Whereas with BDDs, you may have a compact representation. That's why, you are, in this method, you're using this BMC. You remember that? So we are not doing, so we are enumerating parts here, whereas there you are computing images, okay?
Yeah.
You get it?
Okay.
Yeah, so that is the point I was trying to make, okay? So you could do the same thing here, but using SAT solvers, because it keeps things in CNF form, pretty soon the formulas representing ith stitch image we become very big, whereas doing that, okay, become big, and even doing existential quantification elimination itself will, if the formula is too big, okay. Whereas in BDDs, they may have, because the existential quantification elimination operation is kind of quadratic in the size of the BDDs, and if you luck out and then have your image have compact representation of BDDs, therefore you may be able to successfully compute fixed points. Okay, that is one way of doing it. Or another way is to use search for other kinds of inductive invariants. I will do that. So now I want to say something about completeness threshold. Okay, so that is also another way to do it. So what we're doing right now in BMC is something like this. Okay, so we are checking if a formula phi holds on paths in M up to length K. Correct? Yeah. So for finite state models, there is, so there is obviously and this we are doing by enumerating, looking for longer and longer counter examples. Okay, so and longer, and we said with lasso shape. Therefore, for finite state models, now I state there is obviously it is not so obvious. So the claim is that there is always some D, some finite D after which, if phi is true, that you haven't found any counterexample up to that d, some finite d, then it'll always it'll be true for all phi. Okay, I mean for all paths, for all there'll not be any counterexample. Okay, why do you think that there should be such a d? All I've said obvious, but is there any? Would you, Natham, in Paramalai, what do you think? Of course, if for a finite state system, sooner or later, say you define for now. Suppose you define the length of a lasso to be, the longest point before it repeats. Okay, that is the prefix part of it, or from all the way 0 to k, after which it lassos. So say that is the length of the lasso. Okay, so there is always a bound on the length of the lasso. Okay, because but you can actually prove this because because your formulas and since your lasso, there is always a bound on the maximal length of the lasso shaped paths that you can actually have in a finite state system. And if every counterexample has to be lasso shaped, and since your formula is has some finite number of finite height, okay, in terms of your the structure of the formula, you can actually prove that the for all formulas that there is a finite measure, okay, for some d, the length of the counterexample, after which you can guarantee. We will come up, we'll see some completeness thresholds, and as we move along, you'll see there could be looser and other kinds of completeness threshold as well. Now, such a d is what is called a completeness threshold. Okay, that maximal d for any given transition system and the formula, after which, if there are no counterexamples of, you haven't found counterexamples of that length, then beyond that, there will not be any counterexample. There's guarantee that you can guarantee that there will not be any counterexamples to that formula. That is what is called a completeness threshold. Now, that is the definition of a completeness threshold. So if you're able to obtain a completeness threshold, then you can do this kind of thing. Okay, these, as I said, completeness thresholds, they are usually computed as in a property specific way. They're a function of the property and also for a particular transition system, because they depend on the structure of the transition relation in the way that it connects the different states. So the challenge of doing this thing is to come up with bounds that are small enough, even if not precise or tight, the tightest, to come up with some bounds. And if you're able to find that bound for a particular property or any model that you're checking, then you can use this kind of a flow chart. This is just an enhancement of the thing. So you unroll, build bigger and bigger BMC formula instances of the kind that I showed. Okay. And then check for counterexample. If there is a satisfying instance of that BMC, bounded model checking instance of the formula, then you're found it. If not, you check if K, you've reached the completeness threshold, and you keep on doing it. If you have reached the completeness threshold, then you could get out and say that you're done, you're verified. So this is the way to make it complete. Any questions here?
No, sir.
Okay. Now, let's briefly look at, so let me define a few things. Remember that the way some measures for two states that are actually in a Kripke model that are actually connected by path. So remember that the way that, okay, so the way that, SAT-based thing, this thing works is, as you know, symbolic model checking, when you check this BMC instance, you will get all states that are reachable in a certain length in one one SAT instance check, right? Therefore, it is in some sense, getting into that the set of states that satisfy that, all of them that are reachable. Okay, when you check a k-long BMC instance, it'll it'll get all the the states that are connected by that k. So the length of the shortest path between two states, okay, is what I call it as distance. That is the minimum. Okay, there can be two states in a Kripke model, could be connected by several different paths. Okay, which may have repeated states or no repeated states. Okay, but let's the distance of two connected states, S and T, in a Kripke model is defined as the shortest path between those two states. Okay. Now, a reachable diameter is the maximal distance between two reachable states. See, among all states that are pairwise states, S and T, that are connected, it says that what is the maximal distance, okay, for each, over all pairs of states, okay, and that is what? Okay, that is for any two states. Now, the initialized diameter is the maximal distance from an initial state to any state that is reachable from any one of the initial states. Okay, so given a transition relation of a Kripke model and a set of initial states, then the initialized diameter is the maximal distance that any any state that is reachable from any of the initial states, okay, that are connected. And the reason that we're defining it in terms of the shortest distance and then the maximal thing is because when you do this search using a symbolic model checking, that you incrementally check for larger and larger k, you get the if there is something that is reachable through any path with through any path, then you will get it into your satisfiable thing in that thing. So let's look at this example here. Suppose this is the Kripke model. These are the initial states. Okay, that's in green. And your transition system diagram is like this. So what is here shown in yellow are the unreachable parts from the initial state. So the diameter for this thing is 4. Why? See, because there is, that is the maximum distance between any two, whether reachable or not reachable. So that's why here, see the path from 9, 1, 2, 3, 4, okay, before it folds itself. So you can go, so from 9 to 8, okay, is you're only doing from things. So 1, 2, 3, 4 between any two, any two states. Okay, the initialized diameter is 2. The reachable diameter is 3 because this is the reachable part, and the maximum distance from any one of the initial states to states that are reachable in 0 or more steps is this 4. Okay, and that is reachable, although it is from 0. There is from 0. Because from 1 there is a path of reachable diameter is 3 because there is
from 0 to 1, 1 to 3, 3 to 4.
yeah, say that again. Say it
0
loud.
to 1, 1 to 3.
Yeah, 0 to 1, 1 to 2. No, but that 3 is also reachable by.
Yeah. 0 to 1,
Maybe
1
the
to
diameter
3.
is only 2. The reachable diameter, the reachable diameter is between any two states, not necessarily from the initial thing. That's why if you do from, that's fine. So from 1 to 1, 3.
From 0 to 4, it will be.
0 to 4, it's 0 to 4. 0, 1, 1, 2, 3. Exactly correct. Okay, and that's the shortest path between 0 and 4. Since that 4 is also reachable by a shorter distance path from 1, that's why the initial diameter is 2. Okay, and the diameter is from any two states, whether they're reachable or not, and that is 4. Okay, therefore, given this, you can see that completeness threshold for G-like property is the initialized diameter, because when you do this BMC K for larger and larger K, you are getting in one step, getting all the states that are reachable in up to K states, and therefore, you can in two steps you will get you will accumulate all the reachable states. Okay, correct? So you would have once you've reached of length to the initialized diameter. So when BMC 0, you will have 0 in 1. BMC 1, you will have all the paths leading from, you would have accumulated all the paths from 0, 1 to 2, 3. And in the next step, you would have got all the paths from 0, that include that reach 4. Okay, because in BMC 2, you would have at each point you're checking if there is some path, okay, that from any initial state that you can get to that state, and therefore the initialized diameter is the kind of the tightest threshold for invariant properties of this kind, G of P or AG of P. Do you agree?
Yes, sir.
Yeah, okay. So that's the thing. Now, so for G of P, if you can compute this, as you can see that this is certainly this measure, and the diameter is a property of the Kripke model, okay? And the threshold completeness threshold is a function, can be expressed usually as a function of this diameter, a few other measures for different properties, okay? So for properties of this structure, you only need to run this BMC for up to the diameter. And provided you can compute the diameter. There is, how do you a priori compute this completeness threshold. That is a some thing, and we will get to that. I'm not going to discuss that today. I'll actually assign that as a written problem along with your final project, because as I said, programming project, I'll also have some written part, which is, you can say that is like your take-home exam or something like that. Okay, so so that is the diameter. So what I have is, you can actually, okay, I will show. So first I will define another measure, okay, which is this is the tightest bound for safety or invariant properties, okay, for simple liveness properties. See, for simple liveness properties, as you know, that is not good enough, okay, because you will have to look at, the largest sized lasso, okay. You may have to go up to, the largest sized lasso. By size of the lasso, I mean, this is a K-sized lasso, okay. So you may have to, the worst case bound is the length of the lasso. And that's what reoccurrence diameter is defined as, okay. Reoccurrence diameter, radius, is defined as the length of the longest path without any reoccurrence states, okay. The longest that you can go from an initial state without any state reoccurring reoccurring is what is called the reoccurrence diameter. So the size of a simple lasso, okay. So for this, so for simple liveness property, it's enough for you to go till you get a point where there's no states repeating, and then you have lassoed like this, okay. So that is what reoccurrence diameter is. Although you can have lassos with repeated states, for simple liveness property, just finding something in which, because if there is some repeated states, you could remove them anyway, because if something is if that state does not satisfy not of P, then you can actually remove that, and it does not. I mean, you can make another lasso, okay, which with only one occurrence of that state, to and then extract a smaller counter example with a non-repeating a lasso which is pure. Okay, that's why I made a distinction between a pure lasso and an impure lasso. A pure lasso is one in which no states repeats before it lassos. So for simple liveness property, it is good enough to find such a pure lasso shaped counter example. And the reoccurrence diameter is a bound on the largest a pure lasso. Okay. Now the reoccurrence diameter is then a completeness threshold for no. Yeah. And the initialized reoccurrence diameter is the length of the longest initial path from any of the initial state without reoccurrence state. So for simple liveness property, the initialized reoccurrence diameter is a completeness threshold. Now, the initialized reoccurrence diameter is also a bound for safety property. Okay, because a diameter, initialized diameter, this initialized reoccurrence diameter is also a bound. It's greater. It's greater than or equal to actually the size of a diameter for any transition system. And you can let you think about it. Okay. So now the question is, you can compute. You can express these constraints, you can actually use a SAT solver to compute these diameter and reoccurrence diameter. Okay, it's just that they are the kind of formulas that you'll have to do will be, you will have to encode them in an appropriate fashion. But for now, I'm not going to do this, but it is enough for you to understand if a reoccurrence, what the concept of a diameter and a reoccurrence diameter and why they are completeness threshold for safety and simple liveness property. Is it clear as to why reoccurrence diameter is a completeness, is the tightest completeness threshold for simple liveness property? Any question there?
No, sir.
Okay, good. So how you compute, I mean, I'm going to give that as an exercise, okay? And then, as a warm-up exercise before you start implementing your final project. And this is both discussed in the book, and then we can, revisit once you have studied that, okay? All I want you to do is to understand that, okay? So here is kind of an example, okay, to show that indeed the, this is kind of a reoccurrence diameter is see, I mean, this is a instance where the diameter, initialized diameter is much shorter than the reoccurrence diameter. See here, every state is reachable from the initial state in a single step. Therefore, the initialized diameter is 1. Whereas the reoccurrence diameter is n. Because the longest that you can go without reoccurrence is this is kind of the pathological state, okay? In this case, the reoccurrence diameter, which is the longest, the length of the longest pure lasso, happens to be equal to the actual number of reachable states. Okay, the reachable set of reachable states. Okay, I mean the cardinality of the set of reachable states is also a loose bound. Okay, for safety and simple liveness property. But of course, that is not a useful bound to use because it's too loose a bound, and that is bound to be very large. And this is a worst case pathological situation where your reoccurrence diameter itself happens to visit is just as long as the thing. So if that is the case, then you're out of luck. But in some cases, if your transition system is such that reoccurrence diameter, but the reoccurrence diameter is easier to compute, okay, as a problem using a SAT instance problem, but it is certainly larger. It's a looser bound for safety properties. Okay, and this illustrates why it is a looser bound. Okay, and you can actually think about a form of why initialized diameter. I mean, the reoccurrence diameter is actually a bound for the initialized diameter for any transition system. Yeah. Yeah. So any questions here?
No, sir.
Okay. So that is one way of completing. Okay. Now let me come to whatever. Okay, I'll come back to this. It's here. Okay. So do I need to recap the K-inductive next thing, or you are familiar with that? Yeah. Okay, so here, so yeah, if you have any, I'm going to show several different inductive invariants. Okay. So everything that I have marked with a kind of a, this kind of an arrow here. I mean, turnaround arrow is an inductive invariant. Okay. And I made the observation last time that it is an inductive invariant is actually a fixed point. Okay. It's a closure of the transition relation. Now, I made the point that the strongest inductive invariant for a Kripke model, for any given transition relation Kripke model, is the set of reachable states from the initial state of the model. And this is what the least fixed point the using clean iteration method actually computes. Okay, so you start from an initial state, you keep on doing tau until you reach a fixed point. So what I have shown here as reach of I, that's a fixed point, and any fixed point is inductive. Amin, do you agree that any fixed point is inductive relative to T, the transition relation? Why? What is the definition of inductiveness?
For inductiveness, I think if a property is satisfied on a state,
Yeah,
then
the property
its
is
next state also
property.
should.
Yeah, so the property here is what I call as P. Okay, what I've shown here is square box is the entire universe of states representing the predicate true. P is my predicate. Okay, the property. And what I've shown here is, I've shown that this reach I is inductive. Why? It's an inductive invariant. Okay, and the reason is it's it contains I, and it is also inductive because it, as you said correctly, what you said is correct, that every state in that will fold back into itself. Okay, every state that satisfies that predicate, okay, which is reach of I, will every successor of it will fold back itself. Okay. Now, when I compute a fixed point using the greatest fixed point, clean iteration starting from true, which is what we did as the greatest fixed point, which is what we did as a method for doing EG or AG of P. What we did was we started from P, and then we eliminated things that violated, okay, that the tau, okay, that property, and then we arrived at the greatest fixed point, okay, and that is also another fixed point. And that is also an inductive invariant that is strong enough to prove the property P. And that's how, that's another way of, we already saw two different ways. Okay, in that sense, I mean, model checking, traditional model checking is also a way of doing inductive, is an instance, okay? You could call it an extreme instance, okay? So you could do either forward model checking, the computing least fixed point in a forward way is one way, or you can also do, we already have seen that you can use, compute greatest fixed points and then check if my initial state is inside that, okay? Sometimes maybe the counter example to that induction, which is what you're eliminating in each step in your clean iteration, downward cleaning iteration may be shorter to get to the fixed point. So you may converge faster, okay, than doing a forward, tau chain to compute the least fixed point. That's why sometimes, you can do both. I mean, your convergence thing will be, maybe you'll reach the fixed point, faster, okay? So, but image-based, fixed points, we're just looking at these two. What we have seen so far is the least fixed point, which computes kind of the strongest thing, that strongest inductive invariant that is good enough to satisfy the property. Or you could do, this backward cleaning iteration, which is the weakest. But the thing is that you've already seen, okay? But there could be so many other inductive invariants that can be used as candidates, okay? So for example, the ones that I've shown here in dotted concentric circles, I've shown two dotted concentric circles, both of which contain the initial state, both of which are inductive because they are closures. That is, that every state in that, every successor state folds back into it, and they are contained in the property that you want to verify. Okay, so maybe why only use these strongest inductive invariant or the weakest invariants? There are so many. There could be so many other inductive invariants that can be used as candidates, okay, for proving the property. And if you can find a way to get to those invariants quicker, faster through this search, okay, and through an appropriate search mechanism, maybe that will be faster. So the inductive, when I say model checking using inductive invariants, it is really boils down to efficiently, and quickly getting to a suitable candidate inductive invariant. How do you do that is what these various methods of inductive model checking do, okay? Besides these, finding the strongest through least fixed point or the weakest through greatest fixed point, okay? So we will look at three methods. First one is K-induction, okay? Second is what I call as interpollen-based induction. And finally, property-directed reachability, or what I call as IC3, okay? Between now, Friday, and Monday class, we will be covering these three things. And what I want you to do is, what you will be doing is implementing IC3, which is, or the PDR, okay, more generally called property-directed reachability, because they are all concerned with, they're property-directed in the sense they start with the property and then find an appropriate inductive invariance suitable for property. Look at this, computing the reachable state, the forward thing is not property direct. Why? Because you're computing the strongest one. Once you compute the strongest inductive invariant, like the reachability, then you can use it to prove any invariant property, okay, no matter what the P is, okay? That is the advantage of that. That then maybe, but computing the reachable set might be, might take too many iterations using that, and it may be too strong that you don't need it anyway, okay? Now, sometimes maybe AG of P is also very hard. Maybe there are other ways that you can do, okay? So that's the crux, okay? This is very important, okay? To understand what exactly is happening and why, the model checking, traditional, what I keep calling as traditional model checking is finding the thing, okay? So I made 2 points here. So did you understand why, computing the reachable step from the initial state is not property directed? Paramalai?
Yes, sir.
Yeah, why? You said yes, but why? Because you're not using the property at all. You're only starting with initial state, correct? And then you are just iterating and then computing the strongest state. Okay, once you do that, that is good enough for, because that has all the reachable states from the initial state, and therefore for any case, if it is done with respect to relative to the property, then so that greatest fixed point is a property directed way of doing it, because it starts with P and then so therefore yeah, but there are other ways of doing it as well. Okay? So I'm going to take another 15 minutes to at least do.
Sir,
I'm going to take another 15 minutes. Okay.
I have a question.
Yes. Oh, you have.
Earlier you mentioned that this inductive invariance can be used to compute the completeness.
Correct.
K, right?
Yeah. Mm.
How is that done? It is the size of the fixed point as well.
Yeah. So, I mean, that's what, the moment I put together K induction, you will get to know that, okay? So you will have to find, yes, okay, the trick is you will have to somehow, of course, the inductiveness check, along with the enumeration of counterexamples, if there is a check, okay, let me get to the K induction thing. Yeah. Okay. You obviously know through image computation. You know how you reach an inductive invariant. When you reach a fixed point, that correct?
Yeah.
But that's something that you don't want to do when you're doing. If you don't want to do existential quantification elimination, your question becomes relevant. Okay, and the answer is right here. Okay. Answer is right here in this lemma. Okay, so K inductive property is a generalization of an inductive property. Okay, so it's the important thing is this check. Something is inductive, or in general K inductive, if this check is valid. If this check is valid, then this theorem here that I'm saying claims that there always exists a P star such that P star is inductive and P star implies P. And you can see why. Because once you have, this is a way of checking without actually computing the image, okay? Because if there is if this check is valid, okay, which means it says if I assume that, for K steps, if I'm the success, if I start from some state which is inside P, and for K steps, assuming that it is all inside P, that for K plus 1, it will go back into, it goes back into P, then you know that, for all, K, that you have the thing. And the reason is, now you know that you can do a series of existential quantification and elimination of, of eliminating all S1, S1 through SK minus 1, S0 through SK minus 1, then you get it, okay? And that is what is happening. This theorem, okay, this check, inductiveness check, is a sufficient condition to show that there exists an inductive invariant, okay? And to see this, what is happening when this check, this inductiveness check, okay, I think I have it here. When I check, see, this is P, just for comparison, in blue, I have the forward thing. What K induction does is, in addition to the traditional bounded model checking, at each step, it is also checking for each K is equal to 1, it is doing the inductiveness check, which it says, is it one inductive? If P is not, and then T is not, then it is P is not, then P itself is inductive, okay? So there's nothing inside P, the property, everything inside P folds back into itself. And that's what this check. If that is the case, then you're done, okay? If not, then you will increment K, okay? And then see if it is too inductive. If it is too inductive, what you've really done is, assuming that you've removed everything that that is a violation to one inductiveness, you're checking if you remove those things that are violation to one inductiveness. So for example, this one here that I'm pointing to is a violation to one inductiveness because it is leading to something, a successor state, which is not in P, okay? So if I eliminate that, then if I'm too inductive, and that's what this too inductiveness check does. So that is if I start with something which satisfies P, and I take one step and it also satisfies P, then if I take one more step, I fold back into this. If it is yes, then I know it's complete. It is inductive. Okay, so I've reached a fixed point. So that I'm doing through inductiveness check of longer and longer length. Okay, and that's how you keep doing. And for some K, I mean, you will have to find. Okay, you would have eliminated all the violating. I call these states that in one or more steps, states inside P that in one or more steps lead to something which is not inside P as counterexample to induction, CTI, okay? And that's what this induction, this hypothesis in this check is ensuring. If I eliminate it, so because any thing that satisfies the hypothesis is one which would have, eliminated all these counterexample to induction up to that K-1 step. Okay, then it checks if it folds back into it. Okay, so in order to get this, I mean, this inductive invariant, you have to do an elimination of all these things, and that's what was being done in the greatest fixed point. Okay, when you compute the greatest fixed point, you were at each step eliminating, okay, those states from D by taking an existential quantification, okay, by computing kind of the pre-image, okay, and then the image, all those states at that point that took it outside a successor, and then you eliminated that. That was done using, if they're saying, oh, is there a state that satisfies AX of not of P, okay? That if there is a state that all its successors are leading to outside, then you know that you cannot, or even one, if that is leading to EX, okay? Even one, then you should be eliminating it. And that's what, so there what you were doing was, that is in the greatest fixed point method, you were actually eliminating. So, and my soundness theorem is exactly saying the same thing, okay? So if I have this, then I can actually eliminate all those intermediate things that are violation to counterexample, and then construct. And this construct, and that you can is exactly what you did in your greatest fixed point. So the GFP way of doing things is is one way, but the difference here is in K induction. You're not doing pre-image or some existential quantification elimination, but you're doing with a series of checks, okay? Inductiveness check of longer and longer. Does that answer your question now, Paramalai?
Yes, sir.
Okay, so, and that's exactly what so this is the completeness check. Okay, so you're complete, and putting those two things together, you get the K-induction way of completing the bounded model checking method. Yeah, this is exactly, it's quite simple to implement a K-induction. So it is not it is doing checks to see if you have arrived at a point which guarantees existence of an inductive invariant. Okay, the inductive, and this is what the method is. There are two checks here. One is what I call as base check here is what I call as BMC, okay, in the earlier slide, which is exactly checking if there exists a counterexample of length K. Okay, if that is satisfiable, that checks existence of a K-long counterexample. Now, if induct K is the inductiveness check, it checks if you assume that for K minus K long path on which every state satisfies P, the path from some P state, K long path, which every state satisfies P. And if you did one more step, computed the thing, then for every such thing, it is still falls into that. If it falls into that, then you know that it cannot get out of it. Okay, so if the K inductiveness check succeeds, so here you see it's a validity check, okay, which means you have to prove the negation of that is unset. So validity check using a SAT solver can be done by taking the negation of this formula. So make the distinction. This is starting from an initial state. This is starting from an arbitrary P state, okay, that takes it for K long. Okay, that's why in here I have it exactly checks if I got, you know, if I only kept those things that satisfied P, then only, and in one step everything leads to P, and so on, K steps, everything leads to P. If in one more steps, it'll still be inside that. Okay, and that's what I'm doing. So that's what you do. So you start with, you see if any of the initial state violates P, in which case you found a counterexample. Otherwise, you set K is equal to 1, you check the inductiveness check. So K is equal to 1. There you're checking if it is one inductive. If so, you return verify. If not, you increment K and then you repeat. You increment K, check if there is a counterexample of K plus 1. If so, you exit. Otherwise, you check said that this is a sufficient condition. Okay, this theorem that I said, this is a checking this inductiveness check, a K inductiveness check is a sufficient condition to guarantee existence of a one inductive invariant. Okay, and that one inductive invariant is exactly as this picture indicates what you get by computing AG of P. Okay, it's exactly that. Okay, and then as a matter of fact, you're actually doing that, except that you're not doing by eliminating existence of quantifier, but by checking larger and larger long K inductiveness property. Okay, so the reason that it is not complete, that is, this is not necessary, that this algorithm does not actually need not terminate. Okay, when it terminates, this is the worst case thing. I will get to that. Okay, why does it not need not terminate? And that's why it is not complete. Okay, and that is why it is because that inductiveness check is only a sufficient but not a necessary condition. Look at this example. So here is a state. So suppose the property that you're checking is AG of P. See, this state 6 continuously violates the inductiveness check. Why, Amin?
Could you repeat?
I am claiming that, okay, now do you agree that this P is, okay, so P is too inductive here, isn't it? Is P inductive? Let me start with simple question. Is P inductive?
Yeah, yes.
Is it?
Yes.
No. Because it's not one inductive. Say state 4 is a violation to inductiveness. Okay, that doesn't satisfy. I'm sorry. No. Maybe here is P is one. Let's see. Let me. If I start with something which satisfies P. No, P is inductive here. Yeah. P is. I'm sorry. You're right. P is inductive. Okay, it's fine. Yeah, but the inductiveness check I think I was doing with Q. Okay. Sorry, I think I was doing with Q. So forget. So Q is not inductive, correct? Q in this case is not inductive, but it is
Yes.
too inductive. So that is what. Okay. So for P, P is inductive, therefore it doesn't, you don't need. So since PQ is also an invariant, okay, but it is too inductive. It is too inductive, but just doing the inductiveness check, you will not do it because there is always state 6. Always state 6 is, the paths leading from state 6 always fail the inductiveness check. Because for
It go to state 7, right?
Yeah, it'll always, for a longer and longer path that all satisfy Q, there is always a state that violates Q. Okay, but that is not reachable. Okay, that's why just doing the inductiveness check is sufficient but not necessary. Okay, therefore what you'll have to do is you have to strengthen the check that of the induction hypothesis, that it does not have this. This is the case when you have things that that are not one inductive. They're not inductive, but there's some k inductive. Those states, violation to that thing, should not have self loops. Okay, if they have self loops or some looping thing, then this will happen, and then they have one thing going out of it. Okay, so you will get into this kind of a condition. Therefore, in order to make it complete, that it also, if you want to make the inductiveness checks, you have to make the inductiveness check stronger by strengthening the induction hypothesis. You will have to say that those paths should have no repeated states. Okay. That is, we need to strengthen the hypothesis of the inductiveness check with a check that no repeated states exist in the hypothesis. That you will have to add this constraint. Okay, that is. This is a proof of it. So what you have to do is exactly add this. Okay, so here the hypothesis is saying that there is a path, there is a sequence of k long q paths. Okay, on that every state will have to be non-repeating. Okay, it should not have any repeating states. Okay, so then you will not get into this. You will eliminate paths in which these kinds of things will not be there. Okay, so by adding this loopness check, which is a bit, it's a quadratic. I mean, there is a condition that involves pairwise, conjunction of all these states. Therefore, the clauses of your formula will be larger. So once you add that, then it becomes complete. Okay. So P is an invariant of M. There exists a K such that K is inductive. Okay. So that is, with completeness, you have this guarantee. Okay. And I think I have a proof of that, here, so which you can go through and we'll discuss. I think I'm going to stop here, other than saying that, the next method that we will discuss, I'll do it next time. We'll go back to this. Anyway, any questions on this method, K-induction method? Yeah? Any questions? Okay, good. So what we will do here is, the next method that we see is has the idea that instead of computing reachable state, the strongest inductive invariant. The strongest inductive invariant in the forward direction is one in which you start with I. What if you do kind of an over approximation of I? The idea is to get to these kinds of things. The dotted inductive invariance indicated by the dotted circles. So those you can get using the forward method if you started with an over approximation to I. Suppose you started with an I, a superset of I. So if you start with a superset of I and then did the same fixed point iteration that you did for computing the reachable thing, what do you get? And then you will reach a fixed point. At that point, it will obviously contain all the reachable states from I. But since I started with an I, which is a superset of I, it will also contain some other non-reachable sets, non-reachable states. But as long as those non-reachable states are still not violating P, you may get to them faster. Okay, you may lead to a fixed point. Okay, so the idea is, why not start from a superset of I? Now the question is, how do you know what that superset should be? Okay, so if I start with the hope is that if I start with the superset of I and did something similar to what I've done, okay, either through K-induction like way or through image computation, then maybe I will get to something which is weaker than the reach I, and it's a weaker inductive invariant, and maybe getting to that might be faster. Okay, that you converge. That is the idea, or that is the idea. Now the question is, how do I compute a suitable, how do I guess a suitable over approximation as a superset of I? Okay, that will still keep me inside of P, like in this dotted circle. That is what is the first method that we will discuss in the next class. After that, we will discuss a radically different method that does kind of a very different kind of search to get to its inductive, candidate inductive invariant. Okay, so I will stop there. Okay. Yeah. If you have no further questions, then I will end these things. I have to stop share.